Okay, I thought this could go with the electrolysis where we produced hydrogen, and now this is a fuel cell where we're using hydrogen as the fuel. So it's a galvanic reaction, so you're looking at this kind of pattern, spontaneous, and chemical energy is converted into electrical energy. It's an acid fuel cell, so your electrolyte's acidic. Okay, so when we look in our data booklet, you'll find the reactions for this and this. Hydrogen here, this one is your standard half cell. It's the half cell that all of the E0 values are based on. And your oxygen is up here. So these are the two. So because you're getting these out of the data booklet, oxidation and reduction, you must make sure you've got the states. Oxidation is at the anode and oil rig. Cat, anode oxidation is the loss, reduction, cathode is the gain. So the electrons, hydrogen comes in here, the electrons are lost from the hydrogen and then they go around to here and they're given to the oxygen. Oxygen is always the acceptor of electrons, so it's always the oxidizing agent, it's always at the cathode. So it just depends on what the fuel is that's being used. Whenever you think of fuel cells, remember the electrodes are porous. They'll allow hydrogen ions to pass through, but they won't allow the gases to pass through. So they act as catalysts. They help speed up the rate of the reaction, the loss of electrons, and they're expensive because they're made of metals that are being used as catalysts. On the diagram, draw an arrow to show the direction in which these negative ions move. If we're losing negatives from this side, then you're replacing that with negatives to balance a charge. The positive ions would move over here, positive and negative would cancel each other out and balance the charge. A particular cell operates at that many volts, so that is a way of looking at its energy, but how much energy in joules is delivered by 1 mole of hydrogen in this fuel cell? We've looked at a few equations. Q equals VIT. Q equals MC change in temp. We've done with our spirit burner, and we've just done this, calibrating a calorimeter. It may not have sunk in with some people. Q equals VIT. So when you're working out how many joules needed to heat a calorimeter, you use electricity. So this equation will give you joules, and it's got volts in it. The thing is, we don't have current and time, but we know from Faraday's that Q, coulombs, equals current and time as well. So how do we get Q if we don't have current and time? So Q, once you get Q, you normally work out the number of moles of electrons on 96,500. We know that we're getting 1 mole of hydrogen, so we can relate when we're moving, normally when we're doing Faraday's, if we're going from the amount of chemical back to the number of moles of electrons, we can use a ratio. So for every 1 mole of hydrogen, we would make 2 moles of electrons. So we know what the number of moles of electrons is, so we can rearrange this to work out Q. So this comes over the other side, it's multiplied. So we've got 2 moles of electrons multiplied by 96,500, so we can work out that Q must have been 193,000 coulombs. So when you multiply the volts by these coulombs, we're just substituting Q in for IT. Then we get that many joules, convert it to kilojoules, and because this is 2 significant figures, if we put this in standard notation, 1.78 by 10 to the 2, you can round it to 2 significant figures. So it's 1.8 by 10 to the 2 kilojoules. Comparing the energy delivered per mole of hydrogen in the fuel cell and the heat of combustion, calculate the efficiency of this fuel cell. So how do we know how much energy you would get per mole from combustion? So if we go down to hydrogen, you can see that if we completely combusted 1 mole of hydrogen gas, you would release 282 kilojoules of energy. And we've managed to transfer 178 kilojoules of energy, so we've managed to transfer 63% of that energy. So 37% in this particular fuel cell was lost as heat. When you're combusting, if you were to burn the hydrogen in a combustion engine, you would lose a lot more energy as heat. So describe one advantage: less energy is lost. For other sorts of fuels, so like methane or methanol, in the fuel cell you lose a lot less heat compared with a combustion engine. So it's a more efficient conversion. And also, because this is hydrogen and oxygen making water, rather than a combustion engine, petrol driven, you don't make any carbon dioxide. So if we were to use renewable energy to split water and make hydrogen, and then use hydrogen in a fuel cell to produce electricity again, then you've cut out the fossil fuels. The trouble is, the platinum is really expensive, which makes these relatively expensive. Hydrogen is a gas, so it's difficult to store. You need pressurized containers. It's flammable, so explosive, so it's difficult to transport. It could be difficult to produce in large enough quantities for all of our transport. You could produce it on site though, so technically if you've got solar panels you could make your own hydrogen. There's a lack of government incentives, I don't think. I'm just joking with that one, don't put that on the exam, but there's a lack of infrastructure, so we don't have hydrogen refueling stations and we don't have hydrogen cars, so that's a problem at the moment.